And so that what did you get for the speed of sound?
All right, how's everybody doing?
I got some big part. Speed of sound. I got.
Y'all doing all right? I'm gonna get going.
You're doing fantastic.
You're doing fantastic. Fantastic. I'm glad to hear it. That would be great. Yeah, I figure out nobody else is coming in. Or somebody else is coming in. All right, so today, what are we going to do? Test review and homework review. So, has everybody uploaded the homework now?
No, I just
go upload it, please.
2 seconds ago.
Yeah, please do
Okay, I
that.
don't have one of them finished.
No, don't worry. Just do it after class. I mean, I'm going to start grading them. I forgot to put up the assignment box, as you guys noticed, so nobody can turn it in. I don't want to give another extension because I got to stop teaching and do the next thing next week. So get it to me by like class is done at like 2:30. Get it to me by like 3 o'clock. Maybe can give you a little bit of time
Yeah,
to.
I have a couple things I need to punch into a calculator. It needs to be finished.
Okay, so let's go over it. Is everybody ready? So describe what happens when a 5 solar mass leaves the main sequence and enters the subgiant branch. So what all goes on?
It initially slightly contracts, and then starts to expand because the H shell burns.
Which contracts and what expands?
The envelope expands, the core contracts.
Right. The center part contracts, and that releases energy, and everything gets hotter. So the center part gets hotter, and then the envelope expands more because of that burning.
And while it's expanding, the luminosity slightly dips.
Right.
And the temperature cools.
Right. Good. What's happening to the fuel? What's burning?
The H shell.
Is there any helium burning?
Not yet.
Not yet. When does the helium burning start?
After the H shell's done.
After the H shell's done. Okay, is everybody good on subgiant branch? All right.
I put way too much for that guy.
What's that?
I put way too much for that one.
Oh, for this one? That's all right.
It's hard to stay concise.
Yeah,
because you want to justify everything you're saying.
Exactly. So Mark Twain has this. Mark Twain is full of fantastic witticisms, quips and witticisms, quippicisms. And one of the things he said is, "I tried to write you a short letter, but I didn't have time, so instead I wrote you a long letter." Which is really true, because it takes time to make something concise. So, okay, so compute the main sequence lifetime and the subgiant branch lifetime as a. Let me see if my key will open this door. I don't know if my key will open this door. Damn.
I started in at 22.
Yeah, that's cool. As long as you get it to me by 3 o'clock today, I'm good. All right.
I'm pretty sure.
If you've already turned it in, it's a lot.
What about?
Yeah, just
Or maybe I'll just I don't know if more late. Because you don't go like 5 times. So we break it late? We probably don't.
The kids are gonna talk. No, they make. I think I can put up in a
Oh, I feel like you did.
Sorry about not doing that. Okay, so for this next one, how did you guys do computing these bits? Was that horrible?
I was joking.
Okay. What's that?
I don't think that's the chart.
This?
Yeah.
It's not the chart you. This is this
That's
chart.
a different chart.
This is the chart that I made.
Oh,
This is my
okay.
result. So my result is just boiling down that chart to and extracting the things that I want. So this is just the main sequence lifetime. So this is just the column 2 out of that table. And then this is column 5 minus column 4 in years, in mega years. So that column is in mega years. So I got 6 mega years for a 25 solar mass sun. I got 6 million years for its main sequence lifetime. Not very long. I got its subgiant branch lasts for 100,000 years. No, 10,000 years. And the fraction is 10 to the minus 3. For a 5 solar mass star, the main sequence lifetime is like 10 million years. And the subgiant branch is like 300,000 years. And then the fraction is like 10 to the minus 3. And then for a 2 solar mass, they live for a giga-year. They burn on the subgiant branch for a mega-year, which is 1%. So did everybody get numbers that were roughly on that ballpark-ish? You look a little confused?
I still think I used the wrong chart.
Okay, so the chart that you should have used was wrong thing, CNO. That was chapter 13, right?
Yeah, I can see why you'd be confused.
Oh, go on to the other thing. So the table that you should have used was, so it actually shows up twice. So it shows up here in the main body, and then he reprints it down here. Lordo, where is it? This is so long.
I assume that it goes
And then he repeats it in the problem.
Oh,
Yeah. Is this the table that you used? Okay. This is the table that you should have used. But whatever you did do, I'll sort that out. Yeah.
It's a similar idea.
There you go. Hey, can you read that now? Hey, that's nice. I'm compensating for this being super tiny, so I don't even think about that being. Okay, so the second bit, I realized during office hours that there's a little bit of exposition that I need to give you guys about the general outcome of stellar structure and evolution. And I hope most of you tracked it down, but I'm going to write it up. This is something that I should have done, but again, this is the first time through this class for me, so I forgot to emphasize this bit. So the outcome of all of the stellar structure and evolution stuff that we did, so we got 4 equations. You got 4 differential equations that you got to solve, and by waving your hands and jumping up and down a lot, we find these relationships. We find that the radius is equal to the mass in solar masses to the 0.8 times the radius of the sun. So bigger things have bigger radii, but not a lot bigger radii. It doesn't go up like mass. It goes up like mass to the 0.8. The luminosity goes like the mass over in solar masses to the alpha, where alpha changes as the thing goes up, because the luminosity is dependent on whether it's convecting or not. So as the mass goes up, the convection cells turn on and turn off. So this alpha changes. So for, I forgot to write down the so for 2 to 10 solar masses, this goes like 1.4 times the mass to the 3.5 in solar masses. And then the main sequence lifetime, you can approximate this as 10 gigayears times the mass in solar masses to the minus 2.5. So those probably aren't going to show up on the test, but whatever astronomy you do after this, they're going to expect that you know these things. So write those down and pay attention to them. That's how so there's more than one way to do this problem. This is the way that I did it, was by using these scaling relationships. So so the Kelvin-Helmholtz timescale is the energy of the luminosity, and the energy is 3/10 times GF squared over R. R is the mass to the 0.8. The luminosity is 1.4 times the mass to the 3.5. So we just sort out that the energy of, this is for a 5 solar mass star, is 7.3 times 10 to the 48 ergs. That's just from that. The radius is 3.6 solar radii. And the luminosity is 390 solar luminosity. When you plug all these things in, I get 1.6 times 10 to the 5 years, which is on the same order of magnitude. It's within the factor of 2 of the number that more sophisticated modeling gets us. Does that make sense?
How are we supposed to use ergs for this?
As long as you stay consistent.
Yeah, use whichever you like, as long as you're consistent and get something in solar luminosities in the end.
So what would be the luminosity of the sun?
The L sun, I don't remember it off the top of my head, 10 to the 31 ergs, or 10 to the 31 watts. Tell you what, if you want, I can, let me pull up.
Like, I have all this exact setup, but my number is just way bigger.
Well, let's play for a second.
Solar luminosity is 10 to the 26 watt. Right? 10 to the 26 watts.
I ended up with like 10 to
10 to the
12.
26 watts solar luminosity.
I got like 5. What did I do?
3.83, 10 to the 26.
I got
Yeah.
10 to the 26.
I got 10 to the 14.
10 to the 14. You guys are all just saying numbers, and I have no idea what you're talking about.
Solar luminosity.
For what?
In
Yeah,
L?
you said 10
Yeah.
to the 14.
No, L solar in watts.
Oh, in watts. Yeah, it's 10. That sounds right.
Yeah.
I don't remember exactly. Here's what I'm going to do, though. Let's live code some stuff, which is always a terrible idea. But I'll just get you the numbers in better units. Or, well, no, worse units, but the units you did. I have opinions about units. I like astrophysics units because I'm comfortable with those.
It's just they tell you for so long to use SI
I know.
in like every other class.
Yeah, I know. And that's why the book is in SI.
I've never once heard the word erg before stepping foot in this classroom.
I know.
We should go back to measuring everything with football fields.
Good
I
football
know.
fields for eagle freedom.
Fields is the sun away from us.
Whatever you have.
I think we should just like have it in like
Jordan Travis after.
Yeah.
So I actually
yards till Jordan Travis has touchdown.
Measure velocities in Jordan Travis speed.
Jordan Travis units.
How fast does Usain Bolt have to run? I've seen a video.
Okay,
Yeah,
so-
Usain Bolt units.
How many times Usain Bolt's mean speed?
Usain Bolt races.
Okay, so I get
I guess my favorite Usain Bolt's method distribution.
This is much better.
so 48 ergs. What units did you use?
Years.
Yeah, watts
So-
of joules.
10 to the 41 joules. The luminosity that you should have gotten was 391,
Yeah, I got that.
Wait, what? Oh, huh?
or 10 to the 29 watts.
What is that?
I will look at what everybody did and pass judgment. But mostly it comes down to probably you got a unit somewhere wrong. I would super recommend that everybody do all of their homework that has units in it with this package called unit. Sort this out. UNYT or some other thing.
I usually like set stuff up on Desmos and just use the constants I define in Desmos to like.
This one will let you change units without hassle. Because you see
Yeah,
how
I
easy
need to figure
I
out
just
that-
changed units, right?
I
This,
haven't used Python.
no. I'm saying get up this learning curve. Don't make excuses. Get up the learning curve. So okay, where are we at? So I'll look at what you did. Because numbers are always a headache, and I never take off a lot of points for somebody getting the wrong number somewhere. Okay. Supernova has a peak brightness in the B band of 11.7, and then 15 days later it has a magnitude of 12.6. What distance did you get?
Much further than you did. Much less far.
16
No, I
megaparsecs.
got about.
You get about 16 megaparsecs?
Yeah.
Yeah, there you go.
I got that by by a factor of
16 megaparsecs?
Yeah.
It's 16 megaparsecs.
You might have used the wrong little
How
m
many football
at the
fields?
end.
How many
you have
football
to, you have to
fields?
use
Yeah,
the
what-
peak one.
That's what I'm trying to comprehend.
Yeah, so, okay, so
I got
a better way to think about this is to think about how far away things are. So Andromeda, boy, I lost everybody. How far away is Andromeda?
far.
Yeah, how far? Was that? No. How far away is the nearest sun? The nearest star.
Comprehensive far.
That's the nearest star is the sun. The second nearest star is 1
I
parsec.
don't know if the parse,
About.
if you
Okay.
need, you need to add the.
Andromeda is the next galaxy.
Yeah.
That's like a megaparsec.
Oh wow.
But that's just the next galaxy. That's very close.
Okay, so
That's a
that's not-
tiny little part of all of
You
outer
just
space.
didn't know what to do.
That makes sense?
Yeah.
So that's a really important question. How big actually is that?
That's what I have.
Okay, so let's work through it. So we got the Phillips relation, which hopefully everybody looked up, which is minus 21, 2.6, and then delta M15. And this is just 12 minus 11. Yeah, final minus initial, like it's supposed to be. So we get an absolute magnitude of 19.2, and then we just drop that into the distance modulus, and then you get 16 parsecs or megaparsecs. This is one that might show up, so make sure you know how to do that one.
I originally did the algebra wrong with the distance modulus and got something that was like larger than the observable universe, and I was like, yeah, that doesn't sound right.
Good catch.
And I was like, that seems really high. How many parsecs is the observable universe diameter? And it was like,
It's like
less
14
than
times
that.
10 to the
Yeah.
Okay, stellar endpoints for little stars and big stars. Oh, I forgot the smallest one. So that 0.09 solar mass star, what has that done?
White dwarf.
Probably will be a white dwarf, but none of those stars have ever blown up, so we actually have no idea. All of those stars are still in the main sequence.
I looked something up on the internet and it was like 0.08 solar masses.
Oh, it is 8. That says 9. Yeah. So,
Oh.
but still, these stars are all basically still on the main sequence, but they will probably turn into white dwarfs.
Oh, okay, because the one source that was like 0.08 solar masses will just be a brown dwarf.
Smaller than this, it'll become a brown dwarf. It's not a star.
Okay.
I have a question.
Yeah.
So for the 5 solar mass, I was looking up and I might have just looked at the wrong thing, and it might have been the white dwarf mass
Uh-huh.
in solar masses for the Chandrasekhar limit. Is that the white dwarf's mass?
Yeah. So this will
Okay.
this 5 solar mass thing will blow all of its gas off in a wind and a protoplanetary and a planetary nebula. So it blows all that stuff off, and then all you're left with is like 0.7 solar masses.
Okay, cool. I thought it was saying the initial mass, so
Yeah.
I was like, oh, it'll become a neutron star. No,
Right.
it won't. Because
Yeah.
it's, gotcha.
Right. And then the bigger one, what's that?
Sorry.
No.
When I was looking at it, it was kind of saying like that it was in between. So I just put like literally everything. Like I put that it could be anything.
Okay, so
Is it okay?
eight solar masses is the cutoff between being a white dwarf and being a core collapse supernova.
Okay.
So that's really the main line. I mean, really, our knowledge is a little dodgy, but 5 is pretty soundly going to be a white dwarf,
Okay.
and 8 is pretty soundly going to be core collapse.
And then it also kept talking about like when I was looking up, it kept saying about like black dwarfs. Like it goes to.
I don't know what a black dwarf is.
It's
I
the
know, just
it's the
because
end
it's
stage
not
of a white
black dwarfs,
dwarf,
like,
but there
I'm
are
just
none
gonna
because
write
the
that
universe
because I
isn't
never
old
heard
enough.
that. Because I was like, that's not.
Oh yeah, that's just a room temperature white dwarf,
Okay.
I would imagine. Because most white dwarfs have temperatures of like 10 to the 6 or 10 to the 8 Kelvin. They're very hot. But they're also very small and they're not radiating. So it takes a really long time for all that temperature to radiate away. Yeah.
What about 0.09?
What was that?
What was 0.09?
This will be a white dwarf, but none of these stars have ever made it that far.
Oh, I just put that it will be it pretty much forever.
Yeah, this will be it. So at 0.09, if you said it's going to be that for as long as we know, that's also accurate, because those things stay on the main sequence for a really long time.
And when I was looking up for the massive stars, as to necessarily like which one it would kind of do. It was a little bit gray, but it was saying something about like the massive star analog for the Chandrasekhar limit, which is the Coleman, Oppenheimer, Volkoff limit, which was like an initial solar mass of like, what was it? It said like 15 to 20 solar masses of the initial star mass.
Yeah, that's all.
Over that will turn into a black hole. So with 30.
So my official public, and I will call people names and make fun of them for over-interpreting data. The actual data between what these guys are, oh, that should say 30. I just hit copy paste and forgot to change the thing.
Well, one of them, there's also 9. So
yeah,
I think
there's 8, 9, and 30. So all of those are going to be core collapse, and we don't have enough information to say it's going to be a neutron star or a black hole.
So that's what I was going to ask is like, is the TOV limit like a real thing?
I think so. It's a real thing for neutron stars. So it's basically the maximum mass of a neutron star, but it's not actually accurate because we have observed neutron stars that are bigger than that.
Okay.
So Oppenheimer, the other guys,
Tolman, Oppenheimer,
Volkoff, isn't as robust a limit as the Chandrasekhar limit. The Chandrasekhar limit is pretty stout. Yeah.
I put it would be a neutron star for 8 and 9 because the shock wouldn't be enough, but I just put for 30 it would be a black hole because the shock would probably be much greater.
That's how we want it to work, but the science doesn't bear that out. The science is still vague. 30 solar mass could be a neutron star.
Do you think it's more likely to be a black hole though?
I'm not going to make any kind of statements about that.
Wow. Okay.
Oh, because I don't know. Because I don't think anybody's really getting. I don't think anybody's studying that stuff, right? Yeah.
For the white ones, would the ones with more solar masses be more dense whenever they?
Yeah, that's right. Their central density is higher. They're denser and hotter. Okay, let's compute the gene's length and mass by dimensional arguments. Okay, sound crossing time. Just speed over size. And then free fall time. How did everybody do with sorting the free fall time this way? No?
I'm just confused with why all the constants just go away. Is it just we say it's approximately because it's like 0.9 of it?
Well, okay. Let's walk through this one. And actually, I'm going to turn on my camera, which this other side camera is not on right now. So give me 1 second while I turn that on. Because I'm actually going to do something.
Like square root 1/4 pi comes out to like 0.9. So is that why we just say fuck it 1 over root 0?
No, you don't need to do anything. You just look at the dimensions, and
I'm so confused.
it's all good. You'll be less confused in a second.
Thank you.
Is it L over CS or CS over L?
Watch the units.
Meters per second over meter? Wouldn't that just be 1 over second?
Yeah, so that's a typo.
Yeah,
That's upside down. I do that like 100%.
watch the units in question.
Watch the units, and if I screwed it up, then I screwed it up. So okay, so let's talk about this. I didn't belabor this in class, but I probably should have. But what can you do? So I have two quantities. I have G. And what are the units on G?
Newtons per meter squared over
Kilograms
kilogram squared.
per second squared.
Kilogram meters cubed per second squared.
Is that right?
Can you guys show me
I don't know.
Okay, I always forget this, so let's sort it out. F equals G M M over R squared, so I need kilograms meter per second squared equals G equals kilogram over meter squared. So my meter squared goes over here and I get meters cubed. My 2 kilograms go over here and I get a kilogram in the bottom, and I'm left with a second squared equals G. Okay, meters cubed per kilogram second squared. I have to do that because I forget. So that's the units on G. What are the units on density?
Kilograms per cubic meter.
You're like
So density is in kilograms per meter cubed. So I'm going to have G to the A times rho to the B equals seconds. All right? Does that make sense? I'm just gonna make some crap up by putting together the things. This is like sticking your hands in the Legos and just putting random Legos together, right? I'm just gonna say G to the A, rho to the B, and I want this to be a time. So let's plug in all the units and see what the units do. So I got G is going to be raised to the A, so I'm going to have a meters to the 3A. I'm going to have a kilograms to the minus A. I'm going to have a seconds to the minus 2A. And then for the density, I'm going to have kilograms to the B, meters to the minus 3B. And this has got to equal seconds. Right? So, how many meters do I need to have on the, or how many meters do I have on the right-hand side?
0.
None. How many seconds do I have? 1. How many kilograms do I have? None. So on the left-hand side, I need to have the same thing. So here, I only have seconds. So let's look at the seconds. On the right-hand side, I have seconds to the minus 2A equals seconds. So what is A? A is minus 1/2. And I have kilograms and meter. I have kilograms to the A and kilograms to the B. So kilogram to the minus A, kilogram to the B equals 1. So A, how are A and B related? A equals B. Right? So A equals B, and they both equal 1/2. So time is G rho to the minus 1/2. Does that make sense? All I did was accounting. And I get basically the right answer. The only difference is the 3 pi over 32, which is like a half. Right? This stunt gets you most of the way there in basically every problem you're going to attack. So whenever you have a new problem, make the units make sense, and you'll get most of the answer. So we get our free fall time, root 1 over G rho. Sorry, the camera's drifting. It's hilarious.
The duct tape.
Okay, so then how long can a blob be? The length is then this C sound over G rho. You can also think about this. I realized this when I was doing the homework setting system. You could say this is as far as a sound wave can go in a free fall time. Anything bigger than that is going to collapse because the sound wave can't get there in time. So L should be C sound over G rho. And then there's factors of pi. Yeah?
My free fall time was for the radius and the field.
Did you get 1 over square root of G rho?
Yeah.
Yeah, cool.
So it's just basically T cross over 2 is greater than.
You got an extra factor of 2.
Hmm?
You got an extra factor of 2. That's all right. I patently don't care about a factor of 2. Because as long as the thinking is right, there's always a little bit of. So what's the most massive fluctuation from a cloud with temperature T and density rho? And I think actually this part of the problem wasn't in the original problem that you guys got. Is that right?
I don't know.
That's cool. There was a mistake, and this should have been there, but I had it folded in with my solution, so it didn't show up. This is going to be in the solutions that you look at. Don't be surprised because it wasn't in the homework. It was supposed to be. So what's the biggest mass you can support is just 4/3, 4 pi over 3 rho times L cubed. That gives you the gene's mass, which is just C sound cubed over G rho. So the reason that I had that there is because you need it for the next section. But for the next section then, compute the gene's mass for a cloud that has 5 parsecs diameter, a temperature of 10 Kelvin, and a density of 25 particles per cubic centimeter. And I realized that 5 parsecs is actually small for this cloud. Yeah.
What's mu?
Where?
In the CS.
So I just had KBT over.
You
I
said
just had
ignore.
KBT over.
Was that-
protons.
You told me, well, we asked the same question yesterday, you said to ignore me.
Oh, yeah, that's
Shouldn't
fine.
end up in the simplified version.
That's fine, you can ignore me. So you need it, but if you skip it, it's only a factor of 2 that I'm not worried about. So this is the sound. This is the sound. Oh, that can be square. The sound speed should be the square root of this. So the mu is a factor of 2 because it's molecular hydrogen, right, versus atomic hydrogen. But that's it. So I'm not super worried about the mu. Free fall, and I used 3 pi for this one, but that's all right. So I got 10 to the 6 times 10 to the 6 years for the free fall time. You would get 12 times 10 to the 6 years if you didn't use the 3 pi. So that gives us a gene's length of 2.4 parsecs. Our density is going to be 25 particles per cubic centimeter times the mass of the proton. Here I have 2 because it's molecular hydrogen. But again, since I gave you a green light to ignore mu, that's fine. That gives us a gene's mass of about 85 solar masses. Does that jive with basically what everybody did, more or less?
You say KT over mu MP. Why is it not under a square root?
It should be under a square root. There's a typo.
Oh.
Yeah. Because I just did this this morning, yeah.
My gene's mass equation, I think cubed to the row. So it's that, but the row is cubed.
That's not correct.
Well, it's like 3 over 2 instead of 1 over 2. Yeah.
For here?
Yeah.
Yeah, you have an extra row. That is incorrect. Because you need the row here. Because this L has a row, gives you a row to the 3/2. Then you have another row up front, makes it row to the 1/2.
So in this case, you're using 3 pi over 32 in the
For this
free fall
one?
time. Yeah.
Yeah.
So we're supposed to use a different one for this one?
No, it's just how I did it when I was doing the problem. So if you, I'll take how you did it if you did it a similar way. If you had skipped the 3 pi over 32, that's fine.
Confused.
Where are you confused at? Where did I lose you?
The last part.
This part?
Yeah.
Does this part make sense?
Yeah, I mean, I was lost at part B. So
Oh, yeah, okay, let's back up there. So
Okay.
let's talk about the free fall time. So,
I got that, but like
Okay.
coming in, I was lost at part B.
okay.
So we're doing slightly better.
Okay, cool. So the free fall time we get from just the density. That's just something with the density is going to collapse in this kind of time scale. So then what we need to know is we have a blob. Orange. That has some length. And in it has some sound speed. The time for a wave to go from one side to the other is going to be L over C sound. So that's the time it takes for a pressure wave to stop the cloud from collapsing. So I make it a little bit denser. The pressure wave is going to try to get that density back down to the ambient density. Does that make sense?
Okay.
So this is a time, and when this time, so we call this T cross. And if this is longer than the free fall time, then the free fall time is going to win.
Okay.
So the free fall time wins if it's the short one, and then the thing will collapse. If the object is too big for the pressure wave to support it.
So this is when they're equal, that it's at like an equilibrium?
No, this is a critical. It's a critical length. There's not an equilibrium here. It's stable, 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 and then it fails.
Okay.
So bigger than, so we get L genes is C sound over G rho square root. If you're bigger than this, it'll collapse.
Okay.
That makes sense?
Okay, and is that what we're using to solve the problem?
Yeah, so this is
Okay.
the gene's length. So then we get a gene's mass, which is just the volume times the density. Right?
Okay.
So that's just 4 pi over 3 times L cubed times rho. Yeah.
Okay.
So for the mass, shouldn't it be the radius, not the length? So 1/2 of the.
Yeah, once again, it's a factor of 2 that I don't care about.
Okay, cool.
all of these factors of 2.
It ends up a factor of 8.
It does, but
Still not a lot.
so it does wind up, but I want to get the physics connections first, and
Right.
then we'll worry about factors of 2. So getting this as a mass, so turning a length and a density into a mass is important. Yeah.
How does the number density relate to the N in the ideal gas law?
That's the same. That's the same number density.
Okay.
So if we got roughly 1/8 or 1/6 or some stuff of what you got in solar masses, that's like generally correct?
As long as you did something that was sensible,
Cool.
you get points. If you do something that's sensible and then your calculator is drunk and you get really stupid numbers, I really don't care.
That happens to me a lot.
It happens to a lot of people. Really, it's the physics connection.
So I'm pretty sure I got like exactly 1/6 of what you got.
That's sensible. Yeah, so that's all right, as long as you're in the
I think I was at
ballpark.
like 13 solar masses or something.
Yeah, that's a joke.
It says it.
So then the next bit, so everybody at least should have gotten, the second one is a whole buttload bigger. So you should get a factor of like 1,000,000 larger for the hotter one.
Oh, no.
Okay.
Right. Okay. Oh, I gotta scoot it. Okay. Certain cluster of stars has an initial mass function, and this one, everybody gets this problem wrong. And I haven't graded you guys yet, so we'll see. So okay, there's 5,000 stars in the cluster. We have an initial mass function of yon. What's A? What's that?
I still got
Some number.
2,000 even
Yeah, I got
changed my
2,000.
me.
Really? I still get 4192 or 4172.
I get something to the
268, 2648.
5th.
I can't grade your stuff here. I can't see what you did. So when you ask me that you got a different answer, I usually can't see what you did to get there. So that's why I'll grade them later. But did you do this?
Yes.
So the total number is the integral from a half a solar mass to 170 solar masses of A times n to the minus 2.35.
Stupid calculus.
So this integral turns into 170 to the minus 1.35, minus a half to the minus 1.35. Well, I got a 1.35 here, and I got an A. There we at least have something that look like that. Yeah.
I did that, but I got 2,600.
Yeah, that's what I'm getting too.
Yeah.
All right. Well, all right. So that's a factor of 2. Again, I don't care about a factor of 2.
The exponent applies to the like 7 and the 170, right?
Actually, let's do another little live test of how I did the problem.
Because it would have to. Yeah, I think I laid that out terribly. It's fine. Because I laid it out everywhere else just fine. But I need to go back and fix that one before. Well, I haven't done any calculations on these with my calculator done. And I don't want to do that.
So is there a reason you left off the solar mass on your bounds?
That would
That's where you did like 7 to 170 instead of
I can make
7
Tyler
to
do
solar
it.
mass?
I can make Tyler do the calculations before we read them.
So would the answer be?
My mega calculator died.
Okay, like when I first got here for orientation.
Fourth function finance calculator.
You're not.
The fourth, not the fourth function finance calculator.
It's solar power.
Aha! I found
It's
it.
not.
I found the problem. Yeah, 2,648. That's last year's solution. I changed the numbers, but didn't change all of the numbers. So 2,948. I'll fix that number. Oh, is that still?
Most definitely wrong. I think my calculator was wrong.
Fart. Now I got to change this number too. Okay, let's get all these numbers. Okay, so for second one, you should have gotten 2.7%. Okay, so the numbers that are in this document are a little wrong. We'll go update them off this thing.
I got double that.
Yeah. So all right. So for the number fraction, again, I'm not super worried about which numbers you guys got. What I care about is the process. did you do this integral? So the total mass, so we're looking for the mass fraction above half a solar mass, above 7 solar masses. So the first thing you need to do is compute the total mass. You compute the total mass like m times the function, which gives you this integral, and you should get 11,000. And I got maybe a slightly different number. And then the fraction you should get about a few percent.
About 8,000.
8 is all right. And then for the fraction you should have gotten, for the fraction by mass. Oh, did I do fraction by number? Yeah. And the fraction by mass you should have gotten on the order of like 30%. Does that jive? With basically what you got?
I got all the numbers in the Python thing.
You got the numbers in the Python stack? Yeah, these are the correct numbers. The ones in the PDF aren't right. Okay. Does anybody have any questions about not the numbers, but how to do it, the integrals that I did, and how I got them and why I got them?
This is technically both.
Okay, cool.
In the integral, so when you actually compute it, like on Python there, you put in 170 instead of 170 times solar mass raised to.
Oh, ignore the solar mass integral.
Okay.
I mean, you got to this. The unit goes with the number. So if I have 7 there, whether or not I write down solar masses, it's a solar mass. It's in 7 solar masses.
But wait,
The units are just decoration.
is 7 not raised to the negative 0.35?
Which?
Like when you have the 7.
Oh, yes. This should raise everything here.
Okay.
This should raise everything here. Yeah, it's not masses. It's not solar masses to the thing. It's the whole thing.
So if we were using kilograms, we would just get a different A constant?
Yeah. If we were doing kilograms instead of solar masses, it'd be like 10 to the 44, maybe.
You should get the same A, because that doesn't care about mass. A doesn't care about mass. And the fraction you should get is the same. Because I didn't ask about the total mass.
The fraction would be the same, but wouldn't the A be different because you have some giant factor multiplied and raised to 1.35?
You got to change the unit. You got to stick it a Jacobian and change the units on the mass too. So.
So just use solar masses.
Yeah, use solar masses. And then where's the last one? There was a third part.
Yeah, it was the luminosity one that everyone gets wrong.
Yeah, it's the luminosity one that everybody gets wrong, and I haven't graded it to see if everybody gets it wrong. So okay, it fell off my solution sheet, so I'm just going to do it. So how do you do the last one where I asked what's the total luminosity?
Same thing.
Yes.
So let's get the total luminosity. You do L equals the integral from 7 to 170 of m to the 3.5 times a times m to the minus 2.35. Yeah. So this works out to 3.5 and 2.35. Somebody do that math.
Is it negative?
Yeah.
One of them be negative.
Is it negative?
This was positive and this was negative.
Oh, it is.
Oh, I got that. Okay.
Yeah, the luminosity gets brighter as it gets more massive.
That makes sense.
And the mass function goes down.
Is the lower
Isn't there a factor of like luminosity of the sun in there?
Yeah.
Yeah.
is the lower bound 0.5?
Oh, yeah, I asked for the total. I asked for the total. Okay, so did everybody do an integral like that? If not, do an integral like that. So the important bit is this mass to the 3.5 is inside the integral, because I got to do that for every mass. Okay. Is that it for questions? No. This homework just keeps going.
That's awesome.
That's how it felt last night. It was crazy.
I know, right? Describe the spectral classifications and which one is thermonuclear or core collapse. So a type 1A is which?
Thermonuclear.
That's thermonuclear. That's the only one that's thermonuclear.
Yeah.
Tell me about its spectrum. What's in its spectrum?
Silicon.
And
No hydrogen.
no hydrogen.
Oh,
The lack of hydrogen is important. There was this great video game in the 80s based on Hitchhiker's Guide to the Galaxy. It was a text-based game. And while you're playing, you can do your inventory, and it always says you have no tea. So for the whole game, no tea is part of the thing in your inventory. And then you can get some tea, and then you have tea. It's a hilarious thing. At some point in time, you need to simultaneously have no tea and tea at the same time.
Where do you find this? This sounds fun.
It's a really fun
How do
game.
you do that?
What's it called?
I forget. Hitchhiker's Guide to the Galaxy. It was a text-based game. So anyway, no hydrogen is an important spectral feature. So type 1b, also no hydrogen. This one has helium. And type 2p, with hydrogen. That's it. It has hydrogen. The spectra doesn't tell you whether it's P or L. The light curve does. And then the last one. Okay, Eddington luminosity for the sun. So the Eddington luminosity is just 3.2 times 10 to the 4 times the mass. So if you just plug in 1, you get 3.2 times 10 to the 4. So if the sun were shining 1,000 times, 10,000 times, 30,000 times brighter than it was, what would happen to the sun? Was that?
It would get really bright.
It would get really bright, but what would happen to the stuff in the atmosphere? What does Eddington luminosity tell you?
Something about pressure, maybe.
Something about pressure.
Yeah.
So remember, what did we balance?
Low pressure beats gravitational energy.
So just blows
What
up.
kind of pressure?
Force.
It's a radiation pressure.
Photon pressure.
Beats the gravitational pressure. So what would happen if the sun suddenly started shining 30 times brighter?
It would blow out.
It
Blowing
would-
everything away.
It would blow out. It would blow up. So it would blow all the stuff off the surface. And that's what happens when you have a massive star towards the end of its life. They do start to shine close to their Eddington limit, so they do start to blow this stuff off. And the last thing, the Mortlock quasar, which is one of my favorite objects in the universe because it sounds like something you'd find in a D&D dungeon or something. But Mortlock was the author.
I kept trying to look it up to compare it to like the actual value,
Oh.
and I ended up finding it. It's right.
Yeah,
It's
yeah.
like-
If you just Google
No,
Mortlock
it-
quasar, you
it's-
get it.
I was just finding a bunch of
Giant.
papers that were citing Mortlock et al, and I was like, no, I don't care about the paper, and then I just
Me
like,
too.
The way, if you just go to the first archive
that's the
link,
exact one.
yeah, this is the link, and you get this number, because how did they get the mass of this black hole? Same thing. That's what they did. So how big did you get? You got 2.2 times 10 to the 9 solar masses,
Quasar.
which is a really large object. It's also at the beginning of the universe, so we don't really understand why this object exists, but it's really goddamn big. And it's at basically the beginning of the universe, so we don't know how it got there. There's lots of these. And that's it. Okay. And that actually ends my time. Do you guys want to spend 5 minutes on what I think is going to be on the final?
Spend as much time as you need.
Please, please.
Yeah, like do an hour more.
I'm going to just race through it, and this is all free, so if you guys got to go, I'm recording it. So if you have another obligation, you don't have to stick around.
No, I have nothing else today.
Sorry.
Sus.
Too sus. Oh, man. This is the sheet of things that I think I'm going to put on the test.
That's a question.
Good question.
Can I take
Can
a
you
picture of
upload
that?
Right
that
now,
online?
21.
I see
What will
what
be
you're
on the
saying.
test is a subset of this.
How many questions do you think?
Okay, so actually, since I don't have a ton of time, let me just jump to the chase, right? I'm going to jump to...
What?
I'm going to... What?
You can jump far.
That's right. I'm
No
just
way
gonna-
you jump that far.
I'm going to jump to the important bit, and I'm just going to write down the things that I think I might ask. I might ask other things too.
Man.
So this isn't an exclusive list, but it should get you at least the
Can
things.
we see the
Was that-
extensive list online?
The comprehensive list is I can't give you a comprehensive list, but I can give you this one, which will be pretty close. Okay.
What if you just upload a picture of your notes onto
we
Canvas,
see
like
the
that sheet right
notes?
there with all of the
Just-
possible things?
Oh, that's what I'm going to do. I'm just going to write this up.
Okay.
Oh.
So I'm going to write up what I think might be on there. So this is the sheet. I sat down and I wrote down a couple of sheets worth of stuff that I think we covered. And this is actually just what I think so I distilled that down to what I think I might ask. So these are the things that I might ask. This is going to be pretty generic in general. So that's actually what it says, stuff from a star. So distance, luminosity, so all this stuff when I say Delta Scorpius has a temperature of 8,000 Kelvin. What kind of star is it? How big is it? How far away is it? Right? So that kind of question. So this is like distance modulus. Luminosity is r squared t to the fourth. Little m, big M, that kind of stuff. So all of the things that I might ask about observing a star. A lot of that is about distance. So here's a star, here's its brightness, here's its spectral class, what's its distance? So that's the kind of question that I would ask. I'm not going to assume that you have memorized the mass spectral class relationship. I'll hand you any actual numbers that you need. So know how to get things out of a star. The reason that I'm not going through all my notes is because this is like 11 things, but Kepler and Newton. So I'm not going to ask you how to derive Kepler's first law, because that's long and complicated and I haven't asked it of you, but the other ones I think are pretty straightforward. You did just fine in the midterm. So deriving Kepler's laws is good. Using Kepler's laws, really useful. Kepler's third law especially, that's one of my favorites, right? So be familiar with what they are and how to use them. And for some of them, how to get them. This isn't really in a great order. Parallax is up here. Don't forget about parallax. It's easy to review it. Binary masses. There wasn't a lot in that section that I really spent any time on. So the binary section is kind of long, but what's in it are types. You should know what the types are. It's easy to get your head around it. They're self-descriptive. And basically, it's just what can you see? Sometimes you can't see part or all of one of the companions. How do you get information of that? So the types of binaries, and then masses. How do you get mass from a binary star? So the binary star could tell you, just observing the binary star gives you all the information that you need to determine its mass. Diffraction limit. So we didn't spend a ton of time on telescopes. But you should know what the diffraction limit is and how to use it and what it is for some telescopes. Boltzmann equation. And his buddy Saha. So I like these equations. They tell you an enormous amount. They're very, very powerful. Boltzmann equation is foundational and shows up everywhere. So high likelihood there will be a Boltzmann equation.
Do we need Maxwell-Boltzmann?
Yeah, that's a good idea. So the Maxwell-Boltzmann equation. Everything in that chapter, we did that chapter up pretty well. So basically everything in it that you feel like we spent some time on. So know the Maxwell-Boltzmann equation, know the Saha distribution, know the Boltzmann equation, the Boltzmann distribution, and how to use them. Boltzmann, diffraction, binaries. Oh, the stellar stuff. Also the extinction. Well, that's actually. It's a phi. Radiation transport. know how know the radiative transfer equation and how optical depth works, and also mean free path. So this, yeah. Kelvin Helmholtz time, burning time. So we spent a bunch of time. So we spent a bunch of time with atmospheres. So we learned about extinction. We learned about what else did we learn about atmospheres? Let's not talk about that yet. Let's talk about what else we said in atmospheres. We talked about mean free path. We talked about opacity and sources. We talked about the Roslin mean opacity. I'm not going to ask you what the definition of the Roslin mean opacity is, but you should know what it is. And you should know about the sources of opacity. So what are the things that get in the way of photons? How do those things all work together? And then we did interiors. So there's 4 equations. Make sure you're familiar with all 4 of those equations. What all did we talk about in interiors? I lost mine.
Do we need to derive them?
Yeah. I won't ask you to derive any of these. We talked about Kelvin-Helmholtz time scale and nuclear time scale. We talked about nuclear burning. We talked about the PP process and the CNO cycle. Is anything else key on that?
What are we expected to know in terms of PP, CNO, and triple alpha?
Make sure you understand. I'm not going to ask you to memorize every single chain. At least know the one chain for each of these. So the first one, how that works? Yeah.
What is that before PP?
Alpha cubed. Burning. PP, CNO, alpha cubed. So know the basic reaction rates. So at least for the first channel. Not for the other channels, because they're more rare. They're not complicated. Well, no, they're a little complicated, but it's the same kind of procedure. So I might ask, write down the CNO cycle. I wouldn't feel bad about that. But I wouldn't ask anything that's really esoteric about it. Let's see. And then we did supernova. So you should know the Phillips relation. This is a very important relationship. It can't be stressed enough how important this is for our understanding of what's in the universe. Types. Oh, well, I shouldn't do supernova first. I should do late stage evolution first. But in supernova, we talked about Phillips relationship and types of supernova. So be able to describe a type 1A or a core collapse, at least in broad strokes. Yeah, so on the details of the actual supernova, I'll only ask you high level questions. I won't ask you anything that's harder than what I've asked you already. We did late stage evolution, which had all of those bits. So be familiar with each one of the pieces. So there's the subgiant branch and the asymptotic giant branch and the tip of the red giant branch, and the pulsations. And then it's a white dwarf. There's not a ton. There's a couple of steps. But be familiar with the late stage evolution. And then, I'm going to go in the middle. So the star formation stuff, genes in free fall, and the IMF. Really make sure that you know how to do that IMF question. The odds of me putting it on the final are really high. Understand Eddington, luminosity. You should know what it is and the relation. The relation's simple. I'm not going to ask you to rederive it. Just write down 3.2 times 10 to the 4 solar times the mass.
Do we need to know any other Eddington luminosity formula?
No, just that one.
Just the one. Okay. So.
And then you can get everything else from that. But I'm not going to ask you to derive it. So. Burning CNO. Oh, we did stuff with distributions. In general, that goes back to this IMF thing. Yeah, sources of opacity. Bohr model, 13. So understand the Bohr model, 1 over n squared. And the virial theorem, we need that all the time. Anything else? Is there anything else that you think might show up?
Not if you think so. If you don't think so, then we'll be fine.
Can we draw an HR diagram?
Yeah, there might be an HR diagram. You're not by making suggestions here, you're not giving me ideas. I already have all the ideas. But remembering the things that you want to look at, HR diagram. Yeah, that's a good one. So understand not only an HR diagram, but how things move around in the HR diagram. Yeah.
Should I be worried about how to integrate from Gaussian?
A Gaussian, yeah.
Okay.
I would definitely make sure you know how to integrate a Gaussian.
Okay.
But don't let that, do everything else first. Just spend like 10 minutes on it. Don't let that integral kill you.
Okay.
Right? Don't spend a ton of time on it. There's not going to be a lot.
Okay.
But it's a thing you should know how to do.
Okay.
Chase, yeah.
Black body?
Oh yeah, black body. So there's probably a high likelihood that there will be a question on a black body. So again, the black body is a distribution, so I might ask you questions like that. I'm not going to ask you to derive Stefan Boltzmann from the black body because that's a hassle, and it's just math. There's not physics in that. Can I think of anything else? This is a lot.
Distance modulus?
Yeah, that's up there.
Oh,
That was the
okay.
first one.
That was like here.
Yep. Well, that was a long time ago, right? There's a lot of stuff on the.
I know there's a lot that we've been talking about, so it's important to just holler out the things that you think you might. Yeah. Is there anything else that I really think? Let me get just a second. So okay.
Oh.
Introduction, Earth and Space, RA and Deck.
Oh, I forgot those existed.
That was like the first one we did ever.
Might ask about RA and Deck. Usually I've gotten a little bit further towards having an actual final when I do the review. So this is a little.
Are you gonna have office hours or no?
Can we have office hours before the final?
I don't have any scheduled right now. Do you want some?
Yeah.
How many people want office hours? All right. When do you want them?
Monday or
Before
Tuesday?
Monday
Tuesday,
or
before Tuesday. So I have to take
Or
my
Tuesday,
I
because
have
you're
to
taking
take
my test on
yeah.
Tuesday. Okay, Monday at.
After 12. I have a final. 10
You
to
have final.
12.
Okay. Monday at 3.
Yeah.
Does Monday at 3 work for everybody?
No.
Yes, sir.
And
What?
No.
What?
When's your
I have an appointment at Monday at
okay.
2:30.
Okay. How long is it gonna take?
An hour probably.
Okay. Well, I'll probably still be there.
I'll do the one else.
Do you want to do it at 2? We can do it sooner.
Well, no, because it's at 2:30 and I need time to get there.
Yeah, that's fair. You said afternoon.
Yes.
We do it at 1.
Yes.
This game kind of sucks.
We should do like 1 to 5.
I know, if I were just universally available for everybody. Okay, how many, so we'll just take a vote. 1 o'clock?
Can I vote twice?
Sure, yeah, vote twice, by all means. 3 o'clock?
Doesn't matter.
I don't care.
Oh, is it 1 o'clock again? You're the only person who can't make it at 3 o'clock. So I apologize, let's meet, can we meet at 1, well, I'll meet with you for a little bit at 1 o'clock.
Okay.
All right.
Do we need to know like specifics?
We'll everybody meet at
about-
3 or 1,
Yeah.
but 1 will be short.
Do we
Go.
need to know specifics about star evolution?
Yeah, understand this late stage evolution stuff.
Like,
Yeah, the post main sequence.
how do we remember that for like the bigger differences in masses? Do we need to know like differences?
No, just know the first one, just for the low mass one. The book spends a
Just
bunch
the
of time
low
on
mass
1 and
one?
5.
Okay, so just low mass for late stage.
Yeah.
What about because we did a whole section on big stars. Do we need to know about those?
No, I'm probably not going to ask any questions about massive stars. Yeah. Oh, yeah, 1 sheet of notes, just like last time. Okay.
So not like the lowest mass stars where we don't know what they do, but
The stuff that's in the book. Yeah, I mean, there's a section on like 1 and 5 solar masses in the book, where he walks through those. So just work through. You don't have to memorize every step of everything, but he goes through the low mass, the late stages for low mass evolution, and he talks about a 1 solar mass and a 5 solar mass, and he kind of does them both at the same time. But they're very similar. So they're just this. I can open up to it. I can tell. Yeah, everything will be all right. Everything will be okay. But this bit is.
It's like I was going through for the homework. I was going through the evolutions, and I was getting so overwhelmed because it's a giant section in the book.
Yeah, this bit. Yeah, this section it's kind of long because there's a lot of pieces.
Would it be worthwhile to just put that diagram on my sheet?
It wouldn't hurt you, yeah.
Would that be the notes?
Yeah, that's fine.
Or do I need more detail than that?
No, that's all right. I mean, this is good. If you understand, so the things that you need to think about are at each one of these points, and it's kind of complicated, but it's really a process of stuff at the bottom shutting off, and then layers burning, and then they shock the star, so they alter the star. So it's kind of the same thing happens here and then here and then here as stuff turns on. So it's not really, there's a lot of details, but you don't need to worry about the details.
So I just need to know the general, like this here.
Yeah, just like helium core exhausted, core contraction, shell burning, subgiant branch, dredge up from the convection, flash. So it'll take a couple of minutes, but I don't need you to memorize the whole thing, and I'm not going to ask you to reproduce it. So and typically, like very typically, my finals look a lot like the midterm or the homeworks.
So redo all the homeworks.
Redo the homeworks. That should be key.
I'll probably make my sheet and have you look over it on